Welcome everyone to another lecture about complex numbers. In this video, we will discuss the process of determining all roots of a complex number. The process that we'll follow is called DeMoivre's theorem for nth roots, and it should give us all n roots of any complex number raised to the power 1 over n. This is how it works. Assume we have a complex number z in polar form. Magnitude is r and phase is theta. We want to determine the nth root of z, which is equivalent to raising z to the power 1 over n. This can be evaluated as a polar number with magnitude equal to r raised to the power 1 over n and phase equal to theta plus integer multiple of 360 degrees, all divided by n. Any integer multiplier would give us a valid phase angle for a valid nth root of z. But this doesn't mean that we have infinite number of solutions. The unique solutions or roots are only n solutions, and they can be found by substituting k, which is the integer multiplier, for values from 0 to n minus 1. For instance, the 10th root means that k has 10 values, 0, 1, 2, 3, all the way to 9. Each one of these 10 values would contribute towards a unique phase value for one of the valid 10 roots. So, if k equals 0, then the phase is theta divided by n, or theta divided by 10 because n equals 10. If k equals 1, then the phase is theta plus 360 degrees, all divided by 10. And if k equals 9, then the phase is theta plus 9 times 360 degrees, all divided by 10. Note here that regardless of the k value, the root magnitude is always r to the power 1 over n. Let's go through a simple example in detail. We want to find all solutions of x squared plus 4 equals 0. We know that the solutions should satisfy x squared equals minus 4, which are plus minus square root of minus 4 or plus minus j2. But let's see if we can obtain the same solutions when we follow the DeMoivre's theorem. We know that the solution to x squared equals minus 4 is achieved by taking the square root to both sides, giving us x equals minus 4 raised to the power 1/2. Before applying the theorem, the number between the brackets needs to be written in polar form. So minus 4 is written as 4 at the phase of 180 degrees. Now we can apply DeMoivre's theorem. Magnitude r is 4, and the phase theta is 180 degrees, and n is 2. And we would expect two roots when substituting k equals 0 and 1. With k equals 0, we get the first root as r to the power half, which is 4 to the power half, or 2. And the phase is theta divided by n, which is 180 degrees divided by 2, or 90 degrees. So this root becomes 2 at the phase of 90 degrees, which equals to j2. With k equals 1, we get the second root with the same magnitude 2, but the phase is theta plus 360 degrees divided by n, which is 180 plus 360 divided by 2, or 270 degrees. So this second root is 2 at the phase of 270 degrees, or minus j2. These two root solutions are exactly what we were expecting. The validity of these solutions can also be explained graphically on the complex plane. The first root, j2, is this vector here in red, which has a magnitude of 2 and phase of 90 degrees. When squared, we multiply it by itself, giving a magnitude of 2 times 2 equals 4, and giving a phase 90 plus 90, or 180 degrees. In other words, the square is 4 at the phase of 180 degrees, or minus 4, which is the original equation that we were solving. If we look into the second root, minus j2, and square it, we will reach the same blue vector 4 at the phase of 180 degrees. But this time, the phase summation 270 degrees plus 270 degrees has completed a full round and an extra 180 degrees. Let's do a more complicated problem. We want to determine all roots of 2.22 plus j 3.17 all to the power 1/3. Since the power 1/3 means that it is the third root, we should expect 3 roots. We will apply DeMoivre's theorem here to determine the roots. But first, we must transform the base from rectangular to polar form, which gives us 3.87 at the phase of 55 degrees. And now we can apply the theorem. R is 3.87, theta is 55 degrees, and n is 3, which means that the integer multiplier k will have the values 0, 1, and 2. All roots will have the same magnitude of 3.87 to the power 1/3, which equals 1.57. But phases would differ for different k values. For k equals 0, the phase is 55 divided by 3, or 18.3 degrees. And for k equals 1, the phase is 55 plus 360 degrees divided by 3, or 138.3 degrees. And for k equals 2, the phase will be 55 plus 2 times 360 degrees divided by 3, or 258.3 degrees. And these are all 3 roots in polar form. Again, we can have a graphical insight by looking into the complex plane representation. For the first root, the third power will reach the blue vector 3.87 at the 55 degrees with direct addition of phases. But for the second root, the third power will reach the same blue vector, but after completing a full 360 degrees round and an extra 55 degrees. While for the third root, 2 full rounds are completed before reaching the same blue vector again. Regardless of the path, all these roots yield to the same outcome when raised to the power 3, which makes them all valid root solutions to the same outcome. This is all for this video. You can practice what you've learned by going through these problems. And feel free to post your solutions in the comment section. Thank you for watching, and until the next time, stay safe.